Consider our Hamiltonian H defined in a configuration space labeled by the parameter k. In solid-state physics, k often represents the momentum of electrons in a crystal. Now let's consider two distinct points in this momentum space, k1 and k2. These points correspond to two different Hamiltonians, h of k1 and h of k2, from which we can extract the respective eigenstates k1 ket and k2 ket. However, there's a subtlety. In quantum mechanics, eigenstates are only defined up to a global phase. In other words, multiplying by an overall phase factor doesn't affect any physical measurements. So one can then ask the following question. What happens if we smoothly move or transport the eigenstate at k1 to k2 along some path in k-space? As we follow this path, the quantum state evolves continuously at each point in an adiabatic fashion. Just by traversing the path, the wave function picks up an extra phase that depends on how the eigenstates twist in parameter space. This extra phase is what we call the Berry phase, and it's the central topic of this video. To visualize this, think of your quantum state like a vector you're carrying across a curved surface. Naturally, you'd ask, how do I hold this arrow so that any rotation is only due to the curvature of the configuration space? In other words, as you go from one point to another, you want to keep the arrow pointing in the same direction without adding extra twisting. The technical phrase for this is called parallel transport. It ensures that the state evolves in the simplest way possible, avoiding any unnecessary phases and leaving only those dictated by the geometry of the parameter space. Parallel transport ties directly to a geometric object called the Berry connection, which we'll dive into shortly in this video. Now, is this Berry phase and the Berry connection something we can measure? As we shall see, over an open path as shown, the Berry phase is not gauge invariant and thus cannot be measured directly. However, if you traverse a closed loop and return to your starting point, the total Berry phase is gauge invariant and becomes physically meaningful. However, while the Berry connection itself is gauge dependent, there is a local geometric quantity called the Berry curvature that is gauge invariant. In this video, we'll derive the Berry phase, Berry connection, and Berry curvature. Explore how they interrelate, and uncover the profound geometric nature of quantum states. Our aim is to illuminate the intuition behind these mathematical constructs, which often remains hidden behind formalism, and reveal the deep link between geometry and quantum mechanics. Let's dive right in. Chapter 1. Derivation of Berry phase, quantum state adiabatic evolution. Let us explore the standard textbook method of deriving the Berry phase and unpack its geometric elegance. Let's start with the Hamiltonian. Imagine a system described by a Hamiltonian that depends on a set of parameters, represented as a vector r. These parameters define a configuration space, as shown here. Now, let's allow the vector r to evolve adiabatically with time t. This time dependence simplifies the analysis. To understand this, we must analyze the wave function psi after time evolution. The time-dependent Schrödinger equation governs this evolution. Since the Hamiltonian depends on time through r, solving this first-order differential equation is non-trivial. But let's first recall how we solved the Schrödinger equation for a time-independent Hamiltonian. For a static Hamiltonian, the wave function psi is expressed as a linear superposition of stationary states. Here, Cn is the probability amplitude, En is the energy eigenvalue, and Nket is the eigenstate. If at t equals 0, the system is in the state Nket, it will remain in Nket. And the phase that accumulates over time in this case is the dynamical phase. Now, back to our Schrödinger equation with Hamiltonian that depends on time through r. At any given instant t, the eigenstates of the Hamiltonian can be determined, assuming the Hamiltonian depends on a set of time-dependent parameters r. These eigenstates, denoted as Nket of t, are the solutions to the instantaneous eigenvalue problem. Assuming the wave function psi 0 is initially in eigenstate nket, the future wave function psi of t should probably remain in nket of t, but with a phase factor yet to be determined. For now, let's make an educated guess, or an ansatz, that this phase factor is purely the dynamical phase. However, the exponent now includes an integral over time because the eigenenergy En depends on time. The condition under which a quantum system remains in its instantaneous eigenstate during the time evolution of its Hamiltonian, provided that the change in the Hamiltonian is slow enough and there are no level crossings between the eigenstates, is commonly called the adiabatic assumption. To verify whether this ansatz satisfies the Schrödinger equation, we substitute the expression for psi into the equation. Applying the product rule, we separate the terms into the differentiation of the dynamical phase and the differentiation of the eigenstate nket. Now, let's focus on the partial differentiation of the eigenstate nket. Using the chain rule, we can express it as the gradient of the eigenstate nket in the parameter space, dotted with the time derivative of the vector r. This term represents the rate of change of the eigenstate nket. Additionally, we highlight the first term, which we identify to be the wave function psi ket. Thus, we immediately identify that the following expression is exactly the time-dependent Schrödinger equation. In other words, the term describing the rate of change of the eigenstate nket must vanish for the proposed wave function psi to satisfy the time-dependent Schrödinger equation. However, since this condition is not always true, the initial ansatz is incomplete. So what should we do next? It becomes evident that an additional phase factor is required. In his seminal 1984 paper, Michael Berry formalized the idea of introducing this additional phase factor alongside the dynamical phase. This extra phase, denoted as gamma, is now famously known as the Berry phase. To determine the value of gamma, we substitute the new ansatz for psi into the Schrödinger equation. Let's work this out. The partial derivative with respect to t can be handled using the product rule, resulting in the following terms after differentiation. Can you identify the new terms in these equations? Indeed, the new terms are associated with gamma. The remaining terms are identical to those from the previous ansatz, which included only the dynamical phase. For this new ansatz to satisfy the Schrödinger equation, the highlighted terms must vanish. Let's collect these terms and express them as follows. As before, we can apply the chain rule to express the time derivative of the eigenstate nket in terms of its gradient in parameter space, dotted with the time derivative of the vector r. Next, we separate the Berry and dynamical phases from the wave function psi, and rewrite the entire equation in terms of the eigenstate nket alone. We now multiply the equation by the n-bra on the left. Since the time derivative of gamma, highlighted in blue, is a scalar quantity, the inner product of the bra and ket on the left side of the equation collapses to 1. This leads us to the expression for the Berry phase. The integrand contains a term in blue, which resembles the expectation value of the gradient operator, and a term in green, representing the velocity of the parameter r. Using the chain rule, we can rewrite the time integral as a line integral over the path in the parameter space of r. In this form, it becomes evident that the Berry phase depends only on the geometry of the path in configuration space, not on time. This is in stark contrast to the dynamical phase, which is proportional to time. The Berry phase is indifferent to how quickly or slowly the path is traversed. Therefore, the Berry phase can be viewed as an integral defined entirely in configuration space, independent of time. For this reason, it is also known as a geometrical phase. Chapter 2. The Berry phase is real. Let us begin with the definition of the Berry phase, denoted as gamma sub n, which we derived in the previous chapter. This is often referred to as the geometric integral form of the Berry phase. This integral represents the geometric contribution accumulated as a system undergoes adiabatic evolution along a path from R1 to R2 in parameter space. For this phase factor to preserve the probability amplitude, the Berry phase gamma must be real. If it were not, the wave function's norm would change, violating the conservation of probability. Thus the question arises, can we prove that the Berry phase is purely real? To proceed, let us first rewrite the gradient operator with respect to the parameter vector r in a more standard form. The quantity highlighted in red is known as the Berry connection, which we will explore further in the next chapter. Now, suppose the path in parameter space R is explicitly parameterized by a scalar variable s, as we did in the previous chapter. In this case, the infinitesimal vector dr can be expressed as the tangent vector to the path multiplied by the infinitesimal scalar ds. Using the fact that the rate of change of the eigenstate nket along a parameterized path in parameter space is equal to the gradient of the eigenstate projected onto the tangent vector of the path, we can rewrite the Berry phase in the parameterized path integral form. By reparameterizing the path with s, the integral is now expressed in terms of the scalar variable s, rather than the vector parameter r. We will use this parameterized path integral form to prove that the Berry phase gamma n is purely real. Let us start with a basic property of quantum mechanics. The eigenstate nket is normalized. Since the normalization condition does not change as r varies, this equation also implies that the inner product remains constant with respect to s. The derivative of the inner product of the quantum state nket with itself, as the system evolves along the path parameterized by s, must therefore be 0. Let's start with the derivative of this inner product with respect to s. Applying the product rule for differentiation, we obtain two terms involving the derivatives of the n-bra and the n-ket. Recalling that the bra is the Hermitian conjugate of the ket, we substitute this relationship into the product rule and find that only the real part of the expression survives. Since the left-hand side of this equation is 0, this implies that the real part of the quantity highlighted in green must also be 0. This term is precisely the integrand of the Berry phase, apart from the imaginary factor I. Thus, the integrand in the parameterized path integral form of the Berry phase is a purely real quantity. As a result, we conclude that the Berry phase must be real. Chapter 3. In the previous chapter, we explored the Berry phase and proved that it is a purely real quantity. The key question we aim to address here is, what exactly does the Berry connection connect? To begin, let's revisit the geometric integral form of the Berry phase. The term highlighted in red is known as the Berry connection, denoted as A sub n. This is a key quantity that encapsulates the geometric properties of the quantum system as it evolves in parameter space. The Berry connection can be thought of as a vector field over the parameter space. If the parameter space R is described by coordinates R1, R2 to Rd, then the Berry connection can be written component-wise as A1, A2 to Ad. Here, nu labels the different directions in parameter space. Think of the Berry connection as describing the geometry of the quantum states in parameter space. It reflects the local structure of the eigenstate manifold, capturing the dependence of the quantum state on the parameters. I am asking you to think of the Berry connection as acting like a geometric marker that tracks how quantum states vary. This might sound confusing for now, but we will develop these ideas further in this chapter. Let's start with the definition of the Berry connection, but this time, let's use the vector k to represent our parameter space. In solid-state physics, k often represents the momentum of electrons in a crystal. To gain further insights, we will express the Berry connection in a slightly different form. By introducing the projector operator for the eigenstate nket, denoted as P sub k. The Berry connection can then be written in the following form, which highlights its geometric nature, as it depends only on the subspace spanned by the eigenstate and not on its specific representation. Let's add these expressions to our toolbox as we proceed. Using the Berry connection, the Berry phase can be rewritten as a line integral over the parameter space. This line integral can also be expressed in a discretized form, using n discrete infinitesimal steps denoted by the vector dk sub j. Here we replace the Berry connection a sub n with its definition in projector form. In this step, the infinitesimal vector dk has been absorbed into the trace operation for simplicity. Using the finite difference method, we can approximate the gradient of Pn as the difference of the projectors between neighboring points in the discretized lattice. Substituting this approximation and simplifying, the Berry phase can ultimately be expressed in terms of the overlap between eigenstates at consecutive points along the path. This shows that the Berry phase is determined by the deviation of the overlap from 1 as you move between consecutive points along the path. If the overlap is exactly 1, there is no phase contribution from that segment. This expression is often referred to as the discrete Berry phase formula, or the discretized version of the Berry phase. It is widely used in numerical computations and lattice models, where the parameter space, such as momentum space, is sampled at discrete points, rather than being treated as continuous. Now, let me draw your attention to these two expressions. By combining them, we can extract a clearer definition of the Berry connection. Here, the expression tells us that the inner product between eigenstates at neighboring points is governed by the Berry connection. In other words, as we transport the eigenstate along the path in parameter space, the state must rotate according to the Berry connection. This rule for transporting quantum states is called parallel transport, and it underlies the geometric structure encoded in the Berry connection. Let's illustrate these ideas with a simple 2D configuration space represented by kx and ky. Given the eigenstate at each point in the configuration space, one can compute the Berry connection A. Now, let's consider a path C traversing the configuration space, as depicted. The path can be discretized into infinitesimally small steps. Consider two neighboring points in the configuration space, denoted by j and j plus 1, whose displacement vector is given by dk sub j. The Berry phase acquired by moving from point j to j plus 1 is given by the overlap of the eigenstates at those points, -1, as we derived earlier. If we represent the wave function as vectors, then the vectors going from j to j plus 1 will rotate, and that rotation is governed by the parallel transport equation, as dictated by the Berry connection A and the path direction. As the eigenstate evolves along the path in parameter space, it effectively rotates by picking up a local phase determined entirely by the Berry connection. Specifically, the Berry connection acts as a guide for how the quantum state should change to remain parallel to itself along the path. This phenomenon, known as parallel transport, ensures that the state accumulates only the geometric Berry phase, rather than a dynamical phase, a concept that originates in the broader mathematical framework of differential geometry. However, parallel transport does not guarantee maximum geometrical phase along this chosen path. Recall the expression for the Berry phase, which is the projection of the Berry connection onto the path. Thus, paths parallel or anti-parallel to the Berry connection, A, produces the largest Berry phase. In other words, you can imagine A as a wind field. If you walk directly with the wind, you maximize your progress. Conversely, if you walk directly against the wind, you minimize your progress, but the magnitude of the contribution is still large. Lastly, I would like to say a few more words about the concept of parallel transport. It is important to recognize that the parallel transport rule is deeply connected to the definition of the Berry connection. In fact, the two are essentially equivalent. To see this connection more clearly, we can start by Taylor expanding the eigenstate n sub k plus 1 ket, and then substituting back into the parallel transport equation. It naturally reveals how the Berry connection arises as the guiding principle for how the eigenstate evolves along the path. Consider that the k vector can be parameterized by a single parameter s. This parameterization allows us to rewrite the definition of the Berry connection in terms of s, as follows. From this expression, we can derive a continuous version of the parallel transport equation, which provides a clearer link between the Berry connection and the smooth evolution of the quantum state. This line of reasoning leads us to define the covariant derivative, often denoted as ds, which generalizes the idea of a derivative to account for the geometric structure encoded in the Berry connection. The condition ds of the n ket equals to 0 becomes the equation for parallel transport. The covariant derivative takes on other similar forms in the literature. In this context, the covariant derivative ds accounts for the influence of the Berry connection, ensuring that the quantum state evolves in a way consistent with the geometry of the parameter space. Chapter 4. Berry phase and connection. Are they gauge invariant? In gauge theory, such as electromagnetism or non-abelian gauge theories, gauge transformations are changes of the mathematical variables that leave the underlying physics unchanged. For example, in quantum mechanics, the freedom to multiply a state by a parameter-dependent phase is known as a gauge transformation. Physically, it means we can redefine how we measure the local zero of phase at each point without altering observable outcomes. Because these gauge transformations correspond to a redundancy in how we choose to describe the system rather than genuine physical transformations, the physical observables in a gauge theory must not depend on the choice of gauge. This raises an important question. Are the Berry phase and Berry connection gauge invariant? Let's find out. Let n ket be an instantaneous eigenstate that depends smoothly on k. One can perform a gauge transformation of this state by multiplying it by a k-dependent phase phi, where phi is a real, smooth function of k. Now, let's state the form of the Berry connection before the gauge transformation. Under this gauge transformation, we replace the original n ket with its transformed form. Substituting this into the definition of the Berry connection and expanding the gradient term, we obtain the following. This result tells us that the Berry connection transforms under a gauge transformation by acquiring an additional term, the gradient of the gauge phase phi. From the above equation, we observe that the Berry connection is not gauge invariant and, as a result, is not directly measurable in experiments. However, this gauge dependence does not reduce its significance as a meaningful concept. Instead, it serves as a crucial mathematical tool that, despite being gauge-dependent, forms the foundation for understanding fundamental physical phenomena such as the Berry phase and Berry curvature. Now, how about the Berry phase? Given a path C in parameter space, the Berry phase associated with this path is given as follows. Let's consider an open path, with C0 and C1 being the starting and ending points respectively. Under the same gauge transformation, the Berry connection in the integrand acquires an additional term, the gradient of the gauge phase phi. Thus, the Berry phase associated with this open path is not gauge invariant and differs from the original Berry phase by an amount given by the difference of the gauge phases at the start and end points. Since the Berry phase for an open path depends on the gauge phase difference at the endpoints, it cannot represent a physical observable in isolation. The additional term explicitly links it to the arbitrary choice of gauge. However, if the path C is a closed path instead, then the start and end points will be the same. The additional term introduced by the gauge transformation integrates to 0. Thus, for a closed path, the Berry phase is gauge invariant, making it a meaningful physical observable. Chapter 5. Berry curvature is locally gauge invariant. At this juncture, it is helpful to draw inspiration from classical electromagnetism. In electromagnetism, the magnetic vector potential is a gauge-dependent quantity. Its value depends on the specific gauge chosen to describe the system, and it cannot be directly measured. However, we know that the curl of the magnetic vector potential is gauge invariant. Why? Because the curl of a gradient field is always zero. This means the magnetic field B, defined as the curl of the magnetic vector potential, is inherently gauge invariant. The magnetic field provides a local measure of the physically observable field strength in space, independent of the gauge. In the previous chapters, we discussed how the Berry connection acts as a guide for how the quantum state evolves along a path in parameter space, reflecting the underlying quantum geometry. However, like the magnetic vector potential, the Berry connection is not gauge invariant, and therefore it cannot represent a physical observable on its own. Drawing inspiration from electromagnetism, we seek a physical, gauge invariant quantity that captures the local quantum geometry. To achieve this, we define the Berry curvature as the curl of the Berry connection. By analogy with electromagnetism, the Berry curvature must be gauge invariant because the curl of a vector field remains unaffected by gauge transformations. This makes the Berry curvature a physical observable, directly tied to the intrinsic properties of the quantum system. The term curvature in Berry curvature arises from its deep connection to differential geometry, where curvature quantifies how much a space or structure deviates from being flat. In the quantum context, the Berry curvature provides a local measure of the twisting or curving of the quantum state manifold in parameter space. Let's extend this analogy further. Recall that the Berry phase acquired over a closed path C is defined as the line integral of the Berry connection along the path. This expression should remind us of the magnetic flux in electromagnetism, where the flux through a surface is determined by the circulation of the vector potential around the surface's boundary. Using Stokes' theorem, the line integral of the Berry connection over a closed path C can be rewritten as the surface integral of the curl of the Berry connection over the surface S enclosed by C. Since the curl of the Berry connection is the Berry curvature, this Berry phase can thus be equivalently expressed as the surface integral of the Berry curvature over the surface S. Thus, just as the Berry connection is analogous to the magnetic vector potential, the Berry phase is analogous to the magnetic flux. The Berry curvature plays the role of the magnetic field, quantifying the local geometry of the quantum state manifold. A wide range of electronic transport phenomena can be described in terms of the Berry curvature or Berry flux. These include well-known effects such as the Hall effect and its quantum counterpart, the anomalous Hall effect. The Berry flux in these cases refers to the integrated Berry curvature in momentum space, weighted by the occupation of electronic states, often determined by the Fermi-Dirac distribution. The Berry curvature acts as an effective magnetic field in momentum space. It exerts a transverse force on electrons, much like the Lorentz force in real space. This force is what gives rise to the Hall effects, whether in their classical, quantum, or anomalous forms. Unlike a real magnetic field, however, the Berry curvature is entirely geometric in origin, arising from the structure of the electronic wave functions in the crystal lattice. In the presence of a strong magnetic field, conduction in materials often becomes confined to the edges of the sample, leading to quantized electronic conductivity. This quantization can be elegantly described using the Berry flux integrated over the entire Brillouin zone of the crystal. The result of this integration is an integer value known as the Chern number, which characterizes the topology of the electronic band structure. The quantized conductivity, observed in systems like the quantum Hall effect, is directly proportional to this Chern number. The Chern number is a topological invariant, meaning it is a global property of the band structure and cannot change unless the system undergoes a phase transition that closes the electronic band gap. Such topological behavior is not limited to systems under external magnetic fields and has also been observed in topological magnetic materials, a phenomenon called the quantum anomalous Hall effect. The ideas surrounding the Berry curvature extend far beyond conventional electronic transport phenomena. For example, in the spin Hall effect, spin-Berry curvature plays a pivotal role. Instead of acting on the charge of electrons, this curvature governs the spin dynamics, creating a transverse spin current without requiring an external magnetic field. In materials with strong spin-orbit interactions, the spin-Berry curvature becomes a critical factor in understanding how spins respond to external fields or gradients. This has profound implications for fields like spintronics, where the control of spin currents and spin torques is essential for next-generation memory and logic devices. Chapter 6. Differential forms and multibands. In this final chapter, we will briefly discuss the formulation of the Berry connection and Berry curvature using the language of differential geometry, a powerful framework that unifies and extends these concepts. This approach not only clarifies the mathematical structure of these quantities, but also provides a natural way to generalize them to multiband systems. In the language of differential forms, the Berry connection is elegantly expressed as a one form, while the Berry curvature is a two form. A one form corresponds to an infinitesimal line element akin to a mathematical object that integrates along a curve. A two form, in contrast, represents an infinitesimal area element which is naturally suited for integration over a surface. The transition from the Berry connection to the Berry curvature is analogous to the relationship between a line integral and a surface integral. The curvature emerges as the curl of the connection, reflecting the local twisting or bending of the quantum state manifold in parameter space. The wedge product, or exterior product, plays a central role in this formalism. It is antisymmetric by construction, meaning that the wedge of a differential form with itself vanishes. This property is critical for understanding the antisymmetric nature of the Berry curvature. The Berry connection components, A sub I, represent the contributions of the connection along each direction in parameter space. The Berry curvature components, F sub ij, form an antisymmetric rank 2 tensor, encoding how the quantum states twist and evolve geometrically in parameter space. They are defined in terms of the Berry connection components A sub I. In 3D parameter spaces, the non-zero components of the Berry curvature are given as follows, and are often denoted by omega x, y, and z as shown. These components are cyclic permutations of one another, and their antisymmetric structure can be compactly expressed using the Levi-Civita symbol, a mathematical object that encodes orientation and antisymmetry. The Berry curvature is aptly named because it involves second-order derivatives of the quantum state in parameter space. This connection to higher-order derivatives parallels the classical notion of curvature in geometry, which describes how a surface bends or twists. The differential forms formalism also provides a natural way to generalize the Berry connection and curvature to multiband systems. We briefly summarize their forms here. Instead of being a simple vector element, the Berry connection becomes a matrix, with its size determined by the number of bands in the system. Each component of the matrix reflects the geometric coupling between different quantum states and bands. The Berry curvature retains its interpretation as a measure of local geometric twisting, but it now includes contributions that are inherently non-abelian. More precisely, the commutator of matrix. This non-abelian nature arises because transitions between bands create additional structure in the curvature, making it more complex than in the single band case. The utility of differential forms lies in their ability to describe complex geometric and topological structures in a compact and universal way. While we have touched upon the basics of differential geometry, the full mathematical richness of these ideas extends far beyond this discussion. For those interested in exploring these concepts in greater depth, I recommend the book Berry Phases in Electronic Structure Theory by David Vanderbilt and Geometry, Topology, and Physics by Mikio Nakahara, which provides a comprehensive introduction to the geometric underpinnings of modern physics. I provide the links to their latest editions in the video description below.